students? Okay, right. So, first of all we need to know the difference between the BCD number, ASCII value and ASCII in representation. Okay. So, let us take the decimal numbers. The decimal numbers range is from 0 to 9, isn't it? So, in this scenario, if you take all the decimal numbers, okay, so that is 9 numbers, the BCD is also the same. Is this true? Okay. So, the binary coded decimal will also values will also be the same thing, but when it is represented in your binary format, okay, and if you take 4 bits, right. So, it is represented as 0 0 0, 0 0 1, okay, then 0 0 1 0, then it is 1 1, then it is 1 0 0, then it is 1 0 1, okay, 6 1 1 0, you are representing 7 in 7 1 1 0 0 and 9 is 1 0 0 1. Okay. So, binary coded decimal, right. So, this is your representation, right. So, now if you take a number randomly 5 4 or 5 6 I am taking. Okay. So, 5 6 is number, immediately once you see, you will be saying that this is a decimal number, isn't it. So, but actually this decimal number consists of two numbers, that is 5 as well as 6. Okay. So, 5 is placed in tens, the place value of 5 is 10 and the place value of 6 is 1. Okay. So, this is what the scenario is. Okay. For suppose if I am having 156, okay, then 1 will be present in your 100th position, the place value of 1 is 100. So, this is how we are going to interpret a number. Now, if you unpack this, okay, if you unpack this number, if you unpack this number, okay, so 1, okay, 100 times it is going to be repeated, okay, and if you take 5 times 5 times 5 times our 10 is going to be repeated here, okay, and then 6 times the 1 is going to be repeated. So, this constitute your 156. So, 156 we are saying. Now, what we are doing here is, okay, even though this 156 is known to be a decimal number, okay, this decimal number can be unpacked. I am separating the digits. Okay. So, unpacked. Okay. So, once you unpack the decimal number, you are going to get finally your BCD number only. Okay, and representation of BCD number is very much easy in your binary. Okay. So, now if you take 156, so the binary equivalent, you can write the binary equivalent as 0 0 1, okay, 0 1 0 1, okay, 0 1 1 0. So, this is how we can write the binary equivalent for 156. For suppose if you want to actually convert 156 into binary, what we need to do? So, we need to take 156, okay, and then we have to divide it by 2. So, here we are going to get it as 78, remainder is 0. Okay. So, like this the process has to be done, again it has to be represented, then 37, okay, remainder is 1, sorry, not 37, 34. Okay. So, the remainder will be 0. Then again you are going to divide it by 2. So, you are going to get it as 17, okay. Then 2 times, so 8. So, here the remainder is 0, remainder is 1. Then again 2 you have to divide, then you will get 4, 1 and this this is 0. So, this process you know, isn't it. So, 2 times 0, then 2 times, that is 1 time, remainder is 0. So now if you want to write the equivalent for this 1 000 1 000. So this is what the equivalent of binary for your 156. Okay. So representing this 156 in BCD numbers will be easy when it is converted to binary. Okay. So that is what the concept of this complete program is. Okay. So take a decimal number, unpack it and convert that into its equivalent binary. Okay. So this is what is about your decimal and BCD numbers, okay, and its binaries. Now if you take your ASCII values, okay, the ASCII value of 0 is 48, okay, and for 1 it is 49. Now see, so this is the ASCII values for the representation. And one more thing, these ASCII values again we are representing in our decimal format only. Okay. Now if you convert this in your hexa representation, the hexa equivalent for 48 will be 30H, okay, and this will be 31H. Like this it will be proceeded. Sorry, yeah. So here it will be 32H. Okay, I will represent it as 30 only, 31 till 39. Okay, so this is what the actual table represented in your BCD decimal and ASCII in decimal and ASCII in hexa. Right. Now if you draw the relation between your decimal and ASCII value, okay, your ASCII value will be equal to, okay, 48 plus your decimal value. Yes or no? 48 decimal I will make it as, if you want to represent. Okay, or you can call this as a BCD number itself. Is this true? We can call this as a BCD only, since we are representing only the numbers. Okay, and in our microprocessor we are dealing with hexadecimal numbers only. So if you take ASCII number equal to 30 hexa plus, okay, whatever the decimal number you have, that decimal number, or you can consider this as your BCD number. So this is the relation what we have. Okay, so from this if you want your decimal number back, okay, that is your BCD number back, you have to subtract 30 from your ASCII number. Okay, so understood this table. So if you are not unable to understand this, it will be very difficult. I am repeating once again, it will be very difficult to understand the scenario of this programs. Okay, programs are very easy, but the only thing is we need to interpret the results properly. So for interpreting the results, we need to understand this table first of all. Okay, so BCD, decimal, binary, ASCII value and ASCII hexa. Okay, so this is what we have. Now we are going to convert this into our programs. Okay, got it? Right. So now we will try to write one program for this ASCII to. So in order to obtain the binary decimal number to ASCII number. Okay, so we have a decimal number, we have to convert that into ASCII. Take that number and add simply your 30H. Okay, so it represents a simple addition program. Okay, but here what we do is we are going to introduce the concept of procedures. Okay, so what is meant by a procedure? Anyone? So what is a procedure? Procedure means just like your functions in your C. Okay. So in our 8086 the functions are called as procedures, okay, and the macros are also called as the same macros only in our 8086. Okay. So now without wasting time we will go to the program directly. Edit. Okay, I will open the program. SA1.ASM. not this one. SA2.ASI. Okay, so now see here, we have defined a set of BCD numbers here. Okay, so the program goes like this. So this program is your BCD to ASCII. So this is your BCD to ASCII. Okay, so first what we do is we are going to take a set of all the BCD numbers whatever we have. So the BCD numbers are right from 0 to 9. Okay, so the binary coded decimal numbers. So these numbers we will convert it into its equivalent ASCII numbers, right. So first what we do is as usual we are going to define two logical segments. One is code segment and other is data segment by using the assembler directive assume. Okay, and CS, the code segment, is defined as code. Sorry, we are naming it as code, and DS logical segments we are naming it as data. Okay, so in data segment, that is we are going to initialize the data. So once we enter into data segment, okay, so at an address location 1000. So what the data segment will do? So data is the name of the segment, and this segment will start defining the things. Okay, so we are going to enter into the respective segment, and we can we can access the data, or we can give the code also. Okay, since we are dealing with data segments, okay, so we are entering into data segment, and then at an address location called 1000h, org 1000h, okay, we are defining our BCD numbers right from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this I can call it as okay, let it be BCD number only. Okay, and we are going to reserve 20 locations, okay, in order to store the converted ASCII numbers. Okay, the BCD numbers which are converted to ASCII numbers, we are going to store in some 10 locations. For that we are going to reserve some area, and that area we are naming it as ASCII. Okay, and the 10 locations we are defining at an location called 1010h. Okay, so 1010h exactly. Okay, then we are closing the data segment by using end the segment. Then we are starting our code segment. Okay, so code segment we have started, and then we are starting the program. So we are starting the program, and we are writing move ax comma data, then move ds comma ax. Move ax comma data, the data segment starting address is assigned to ax register, and that address we are moving it to data segment register, ds register. Okay, then we are taking an source index register and pointing to BCD. Okay, where our BCD numbers are located, there we are going to point with BCD. Okay, and then we are taking a destination index register, and we are pointing that to our ASCII locations. Okay, so where we are intend to put your ASCII numbers, ASCII values. So there we can store it. There we are going to point it. Next, we have 10 numbers, isn't it? So we are going to put a counter CL register to which we are going to assign 10. Okay, so 10 you can write. If you write simply 10, it will be converted to hexadecimal and it will be stored. Okay, for suppose you want to enter the number in hexadecimal itself, you can make it as 0A, 0AH. Okay, and then the most important, the concept of procedures. Okay, so by using a call instruction, we are going to a location called B2A. Okay, so we are going to a location called B2A, right? So that is your BCD to ASCII. For reference I have given. So this now the control will transfer from this location to this location. Okay, so B2A. Now this B2A instead of making it as a label, what we are doing is we are defining that as a procedure. Okay. For that, the required assembler directive will be PROC. Okay. So, PROC is the assembler directive which specifies, okay, the code as a procedure. Okay. So, now within this move AL comma at SI. So, at SI, where SI is pointing to BCD location. Okay. So, to this BCD location, from BCD location we are taking 0, okay, and we are moving copying that value to AL register, right. Now, what is our concept? Simply the BCD number, if it has to be converted to ASCII, simply we have to add 30H. Okay. So, that will do the things. So, we are going to add AL plus AL comma 30H. So, this 30H, if you want to represent in hexa, you have to represent it as 30H. Simply, if you want to represent it decimal, you can write it as 48. Okay. Both are same. Okay. So, I will go with 30H. Then what we are doing? So, whatever the converted value is there, that we are moving it to the ASCII location. Okay. So, which is pointed by DI. Okay. With the help of the instruction move at DI comma AL. Then what we do? The next number has to be converted, isn't it? So, increment SI, then increment DI, and then from returning from the procedure, we are using an instruction called RET, return. So, once the control sees the return, the control will be transferred to this location, okay, call B to A. Then what we are doing? Okay, so, we are decrementing the CL value. So, means one number has converted, isn't it? So, once one number is converted, so we are reducing the count by one factor, and now it becomes 9. Okay, then we are putting a loop, okay, and we are checking the condition of CL. If it is not 0, again we are going to call the procedure, the same procedure. Okay, instead of writing 10 times the same command, what we are doing? We are defining it as a procedure, and 10 times we are going to call it by putting a counter. Okay, so now again it will be called, and now the second value, that is 1, will be transferred to AL register, and to that 1 we are going to add 30, such that we will get 31. Okay, and then that 31 is moved to DI register, to the location specified by DI, and again we are going to increment SI, then increment DI. Okay, so like this 10 times this procedure is going to be called. Okay, and by the time CL becomes 0, all the numbers would have been converted to its ASCII numbers. Okay, and then we are going to end the program at by using the breakpoint interrupt, that is INT 03H. Okay, then we are coming out of the code with the help of from code segment with the help of code ended statement, and we are going to end our main program by end start. Okay. So, this is your program. So, now what we do is we will see how the numbers are going to be stored, and how the results are going to be interpreted. Okay. So, for this, as usual, use the MASM command for unassembling the program. Okay. So, we have an error. Okay. So, extra characters on the line, the first line we are saying. So, let us remove that error. Yeah. So, this is there, right? So, let us say how it is going to do. Again, if you get error, okay, the same error we are repeating. So, better I will remove that. I am just trying to give some comments, that is it. Yeah, the same error we are getting, better we remove that line. Okay. So, yes, yeah, now it has been free from errors. Okay. So, then what we do, link the program properly. Okay. So, we got an no stack segment error, sorry, warning, and then go for debug sa2.exe. Now unassemble the program. Okay. So see, your program actually ends at 0014, but the procedure is present in a location called 0015, and it is going to, the procedure is going to end at 001D, means till this your program is there. Okay. So the first line represents, the first column represents the segment address, second column represents your offset address, then B86A07. Okay. So this column is there, right? That column is known as your opcode, then followed with mnemonic, the operation, and followed with operands. So this is what is known as opcode sheet. Okay. So this you have to represent in your records. Okay. That depends how we are going to do. Okay. So now let us say check our result, check our data. Okay. So we have stored 00, 01, 02, 03, 04, 05, 06, 07, 8, 9 in the locations 1000H. Okay. So now execute your program. Okay. So after execution, you just check whether we are getting the ASCII numbers or not. The ASCII numbers are found in address location 1010. Okay. Now see. So in 1000 location it is 00, and its equivalent ASCII number is found in 1010. Okay. In 1001, 01 number is there. Okay. And it is its equivalent ASCII is found in 31. Okay. And here one more thing what we need to observe is, if you take the right hand side, rightmost side, you can see the equivalent ASCII numbers for 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. Okay. That numbers will be repeated. That is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is one reference. Okay. You can validate that whatever the result you have done is perfect. Okay. Now this is about your simple program. Okay. What if the number is given in terms of a decimal number, a 2-digit decimal number? What we have to do? So as said, your BCD, yeah. Yes, Chandramohan, I am not getting. Can you repeat that?
First, we need to convert to binary, sir.
Okay. No. First is we have taken a BCD numbers, set of BCD numbers right from 0 to 9, and we are converted to ASCII. Okay. Now the question is, what if the number is say some 59? What we have to do? This is a pure decimal number. Okay. So this decimal number has to be converted to its BCD numbers. Okay. So that BCD numbers are 5 and 9. So we need to separate them. Okay. So this process is known as unpacking. So here unpack, no, we have unpacked. So like this we need to unpack this. Okay. So what we have to do? Take 59. Okay. Unpack this number into two numbers. Okay. So one is 5 and the other is 9. Now can you tell the logic how to obtain this? It's quite easy. 59 is my decimal number. Now we need to separate them, unpack the numbers into 5 and 9, and to this we are going to add 30H. Okay, 30H I am telling. Okay, so here also 30H we will be adding, so that the ASCII numbers for this 5 and 9 will be 35H and 39H. This is what the result we want, but we can do this. Okay, so but we can do this addition program just as the previous, but the thing is we need to unpack this number. That is the most important thing. Okay, so first what we do is 59 you take, Okay. First, I'll take 59 here. Okay. And to this, I will do the logical AND operation with 0f. Okay. Now, what will be the result? What will be the result of 59 logically ANDed with 0f? It is 09. Yes or no? Still confusion in this? Take any number, okay. If you do logical AND operation with that f, okay, you will have the same number. Okay. Now we want 5. So what here we do is, there are many methods, but I will go with the more conventional method. Do the same logical AND operation with f0. Okay. So once you do f0, we are going to get 50h. Okay, 50 I am calling it as. Okay. So 50 we will be getting, and to this 50, okay, what we do the shift left operation, shift right operation 4 times. Okay, shift right operation 4 times for 50. So now we have 50. So what is 50 in binary? 0, 1, 0, 1. So sorry. So I will make this. I require 8 locations. So what I do? Okay, so I will take this 8 locations. So 50 can be represented as 0, 1, 0, 1, 0, 0, 0, 0. Okay. So now 4 times we have to shift. So for the first shift, okay, so these numbers will be represented like this, and this is your empty space, and we are going to load 0. So this is for your first shift. Okay. First one SHR, right, and then for the second SHR 2 times it is going to be shifted. Okay, so 2 times in the sense like this. So this 0 will come here, and in the empty space again you are going to load 0. So this is for your second shift, and for third shift again we are doing one more shifting. Okay, so where these 2 zeros are appended zeros and one empty space, and again we are going to append one more 0. Okay, and for the fourth shift what happens? So this will be your result. Okay, so these 3 zeros are appended as usual, and in the empty space we are going to have 0. So now what is the value of this after 4 shiftings? This 4 zeros is your 0, and this 5 zeros, this 0 1 0 is your 5. Now you have extracted 5. Yes or no? So this 5 0 you are representing in binary like this, and after 4 shiftings what we got? 0 5. So 0 5 you got. Okay, so this is how we are going to unpack the number. Okay, so this is known to be your unpacked number for our 59, and to this if you add 30 we are going to get its ASCII numbers, ASCII equivalents. Got it? So hope you understood the logic. Okay, so now our program is extended version of this BCD to ASCII. Okay, so let us open that program. Okay, so So I'll open the program. Since I have written the programs, I have showing you directly. Okay. So now see here. Now one more thing here. Interrupt, if you give 56 as directly 56 decimal directly to our microprocessor, what it will do, you know, that 56 will be converted to its hexadecimal equivalent, and for that number we will get the ASCII. Okay. So you have to be very careful when giving the input. So 54 decimal if you want to give, you have to fed the microprocessor that number as a hexadecimal number only. Okay. So what the number we took? 59. Okay. So in the data segment we are defining 59. Okay, by it is assigned with a variable called DEM, and in the ASCII location, since we have taken two numbers only, okay, so two address locations we are going to store. Okay, so that is ORG 1000H, right? And now here also we will be using the same procedures only. Okay, so first line we are going to assign the data segment to your data segment, okay, register, and then move SI. So SI is pointing to the decimal location DEM, okay, and ASCII is pointing by our DI register, that is your destination index register. And since we require 4 shiftings, what we are doing is we are taking a CL register, into that we are loading 04. Okay, and then we are calling the procedure. Okay, so we are calling the procedure B2A. Okay, so in the procedure here I have added one more word by the name called assembler directive by the name called near, NEAR. Okay, so this near defines the type of procedure, whether it is within the code or sorry within the segment or outside the segment, that will be defined. That will be defined by this near. Okay, even if you are not using this, that doesn't matter. Okay, so we are ensuring that the procedure is locating in our code segment only. That's why we are defining it as near. Okay, so B2A is being called defined as a procedure. Okay, then we are taking the number into AL register, means what, which is the number 59. So 59 we are taking to AL register, and to this AL register we are performing AND operation with 0F. So immediately we will be getting 09. Okay, and that number we are going to store at a location pointed by DI. Okay, so even though we have reserved 2 memory locations, I will make this as some 10 memory locations. So nothing wrong in it. Okay. So now what happens? DI in DI location 09 is there. We have unpacked it. Okay, and to this number we are adding 30 to get its equivalent ASCII. Okay, and that number we are storing in DI plus 1th location. Okay, so DI is pointing to 1010. Okay, so now we are moving that value AL, that ASCII value, to 1011 location. So in 1010 location we are storing the unpacked number. Okay, and then we are locating here its equivalent ASCII number. Then again what we do is we take the same 59 number and we are moving it to AL register, and we are doing logical AND operation with F0H such that we will get 50. Okay, and then that 50 we are loading in one more location. Okay, and we are shifting that 50 by 4 times. So CL is defined as 4. So we are shifting right the AL by 4 times. Okay, such that we will get 05. Okay, and that 05 we are moving it to DI plus 3 location, and to this we are adding 30 to get its equivalent for 05. So equivalent for 05 will be 35. Okay, and that we are storing in DI plus 4th location. Okay, so the unpacking process results as well as its equivalent numbers are obtained in DI locations. Okay, so for your better understanding, first I will show you what if if I am giving just it as 59. Okay. So, I will save this, I will execute this MASM SA2.asm. So, can anyone tell me what is the equivalent for 59 in hexa? It will be 3BH. Okay. So, again B is not a BCD number. So, again we will be having a confusion with that. Okay. So, but for understanding the context I am just showing you. Okay. Always remember the inputs should be in terms of your BCD or ASCII only. You should not use your hexadecimal formats here. A to F you should not use as your inputs. Okay. So, link SA21.obj, right. So, then go for your debug SA21.exe, unassemble your program and just check in your data segment how the data is stored. We are given 59 without any extension. We are not specified it as H. So, defaultly what it will do? It will consider that as a decimal and it will be converted to hexa and it will be loaded into your memory. See. Somewhere some mistake has done. So, let me check it. Edit SA21 dot ASM. So, 1000. Yeah, save this. Okay, so now let us see. Let's see. Sorry. Link SA21 dot. I will do it once again. So, MASM SA21 dot ASM, then link the program SA21 dot obj, then debug SA21 dot exe. So, unassemble the program, then check 076A colon 1000. So, now see 3B. Okay. So, this is a problem. So, that is why we have to feed your input as the same. So, I will do the same thing now 59 H. Okay. Then link SA21 dot obj, then debug it SA21 dot exe, unassemble the program. See, our program is going beyond. So, once again press U such that you can see the last line of your program, that is your return. Okay. So, now check your inputs 6A. So, your input is 59 as it is there. Okay. So, now what we do, execute it, okay, and then check your result. See, 59 was my number, first 9 from 59, 9 has been extracted in 1010 location, you just see. Then that has been converted to its equivalent 39. Okay. Then 59 we are taking, first we are doing the AND operation with F0, so that we will get 50. Then it is shifted to right hand side, we get the result as 05. Okay. And then to that 30 we are adding, we are getting the ASCII number as 35. Okay. So, this is how we can interpret. If you want to give any other number, okay, so you can give the other number also here, nothing wrong in it. Sorry. So, it is 076A colon 1000. So, I will give some 64. Okay. So, now execute this program. So, it should be 36 and 34. Okay. So, display your memory, see 34 and 36 you got, right. So, this is how you can do your ASCII to BCD or ASCII to decimal. Okay. When it is asked in terms of decimal, you need to take a packet number and you need to do this. If it is asked in terms of a BCD number, Okay, so you can do the first program, right. So next is the other process, the reverse process. Okay, so reverse process is very easy, right. Instead of add, you have to put subtraction, and the input numbers that should be fed should be your ASCII numbers. Okay, so this is known to be your ASCII to BCD. Okay, so our input should be an ASCII number. So all the ASCII numbers we are defining in the data segment. Okay, like 48, 49, 50, 51, 52, like this. Why I have defined this? Okay, so once you define this, it will be converted to its hexadecimal equivalents as 30H, 31H, okay, 32H, like this till 39H. Okay, both are same. So to understand the context clearly, I have mentioned it as ASCII numbers 48 to 57. Okay, right, and I am interchanging the things, that's all. So in the data segment at 1000 location, we are putting an ASCII number. Okay, we are putting the set of ASCII numbers, and in 2000 location. So why to take 2000 location? So 1010 itself we will use, so that we can see the result, the same block itself. Okay, so ORG 1010. So there we are defining the BCD numbers. Okay, and we are ending the data segment by data endes. Then code segment we are taking. Okay, move AX comma data, move DX comma AX. Okay, then SI is pointing to the our input numbers, that is your ASCII, and DI is pointing to the BCD number location, and 10 numbers we have. So we are putting a counter CL with 0AH, and again we are using the same procedure method. So call A to B. Okay, so we are going to a location called A to B, and there we are defining a procedure. Okay, so what this procedure will do, it will take the ASCII number and it will convert to its equivalent BCD number. Okay, so first take that 30, so 48 in the sense 30H, it is moved to AL and it is subtracted from 30H. So the result will be 0, and that value we are storing in BCD location, the first location of the BCD. Then go for the next, in order to access the next number, increment SI. In order to go for the next address, destination location, increment DI, and return to this procedure, return to your main program. Okay, so after that decrement the value of CL by one time. Okay, and then if it is not 0, again call your function, again call your procedure A to B. Okay, so like this 10 times it will be done, and we will be obtained with our BCD numbers. Okay, so now let us see what we have done. Okay, so MASM SA3.ASM, so link SA3.obj, then debug the program SA3.exe, unassemble the program. Okay, so you can see the data segment. So let us check what is happening in our input side. See, no need to convert actually. Okay, so directly you will get its equivalent numbers when if you see the rightmost side. But why we are writing this program is to understand the context. Okay, so now we will execute it. Okay, and again we try to display the number. Now see, for 30 it is 0, 31 it is 1, 32 it is 2, 33 it is 3. Okay, and 34 it is 4, 35 it is 5, like this it is keeps on going. Okay, so understood this?
Yes, sir.
Okay, so now our next thing is, I have two ASCII numbers. Okay, I have this 35 and 39. Okay, I need to get my decimal number, means ASCII to decimal. Now what we have to do? the logic is reverse. What we need to do? So, these two ASCII numbers are there. From these two ASCII numbers, okay, we have to subtract 30 and 30, so that we will get the unpacked BCD numbers. That 05 will get, 09 we will be getting. Okay. Now, packing is your wish. If you want 59, okay, simply what you do is do the left shift operation by 4 times. Okay. So, once we do the left shift operation 4 times for this 5, you will get 50. Okay. And then take this number and do the OR operation to this A. So, what will be the packet number? 59. You will be getting the decimal number, right? So, packed decimal number we will be calling it as packed decimal. Okay. This is one way, but if you want 95, okay, then you can shift this 9 by 4 times. So, now it will become 90, and to this take this number 5 and do the OR operation. You will get 95. Okay. So, when you have two ASCII numbers, the possible combinations will be two packed decimal numbers. Okay. So, this is the logic what we are following, simple, the reverse process what we have done for the previous thing. Okay. So, we will go to the program again. Okay. So, even then even that also is done. Okay. So, what I will do is edit SA31.ASCII. Okay. So, here I have taken 34 and 39 as my ASCII numbers. Okay. So, the output will be either 49 or 94, that depends upon what the logic you are going to follow. Okay. So, which logic I have followed? So, I have followed first I take 34, okay, and then 34, yeah. So, 34 itself means 49 I am going to get. See here. So, first two ASCII numbers are defined here, 34 and 39. So, we have to get the output as 49. Okay. So, for this I have reserved some locations, 10 locations for seeing the operations stepwise. Okay. So, that is at DEM, and coming to the program. Okay. So, the main program. So, first we are accessing our code segment by using these two instructions, move AX comma DX data and move DS comma AX. Next, move SI comma offset ASCII. To this location we are making our SI to point, and DI to point to the destination location where our decimal number will be obtained. Okay. Then I am taking CL with 04 for shifting operations. Then we are calling it as it is ASCII to binary, right? ASCII to BCD, okay, or decimal. I will write it as D. It will be clear. Okay. So, we are naming that procedure A to D, and first 34, SI is pointing to 34 now initially. So, that 34 is moved to AL, and we are subtracting 34 with 30. So, we will be getting 04. Okay. That 04 we are shifting 4 times. Okay. We will get 4, and that value we are moving it to DI plus 1 location. Next, the same value we are moving it to BL, so that we have to do the last OR operation. Okay. Next, move SI, move AL comma SI plus 1. So, we are accessing the second number 39H clearly, and this 39H again we are subtracting it from 30. So, now it will become 9. Okay. Next, this 9 we are moving it to DI plus 02 location, and we are performing OR operation between AL and BL. So, BL is 40 and AL is 09. Okay. And the operation results to 49, and that data we are going to store in DI plus 03 location. Okay. So, this is what the program is, and we are going to end the code segment by end s, and we are going to end the main program by end start. Okay. So, then save this and perform SA3 event.asm. So unassemble the program. So it is free from errors. Link sa31.exe, sorry, .obj, debug it. So debug sa31.exe. So unassemble the program. Okay, so till C3, that is 002B, your program is having. So let us check our data segment. What are the inputs? So we have given the inputs as 34 and 39. You can see here 49 as your output. Okay, so now we have to get that. So take execute it and now display your memory. Now see. Okay, so 34 and 39, right? And first for 34, the equivalent ASCII number is 4. Sorry, equivalent BCD number is 4. Okay, and then it is being shifted as by 4 times to the left hand side. So 40 we will be getting, and we take 39. So 39 we are ending with F0. So we are 0F. We will be getting 09, and we are doing the OR operation between 40 and 9, so that we will get 49. So now I will just interchange these numbers. Okay, so that we will get 94 as our output. Okay, so edit 076A colon 1000. So here I am giving 39 and 34. Okay, so these are the inputs what I gave. Now execute your program. Now check your display. It will be 94. Okay, so these are the 4 programs what you have to be aware of, right? So any doubts in this?